Hello, everyone. Let's wait for a couple of minutes till more people join.
Ignacio.
Hi,
Everyone.
Hassan. Can you see my screen? I'm sharing the presentation.
Yes, I can see.
Okay, thanks. Should we begin, Hassan?
Yes, I think we have enough number of participants. We can start.
Okay. So, hello everyone, and welcome to this webinar on Introduction to Design Verification. My name is Ignacio from the Barcelona Supercomputing Center, and I'm joined here today by Hassan from 10x Engineers. And over the next couple of hours, we are going to explore what design verification is, why it is so critical, and how it shapes the modern chip design industry. Before beginning, we would like to introduce ourselves. Um, as I mentioned, my name is Ignacio. I'm a design verification engineer from the Barcelona Supercomputing Center. And also, I am an associate professor at the Autonomous University of Barcelona. I have a master's degree in computer and electrical engineering. And right now, I'm working on design verification of RISC-V cores and accelerators. Hassan, would you like to introduce yourself?
Yes, sure. Thank you, Ignacio. So I'm Hassan, currently working as staff engineer with 10x. I'm by profession, I'm DV engineer, and I'm leading a team, and we are working on the verification of RISC-V cores. I have experience with the verification of IIML accelerators and memory subsystems, Uncore IPs, and my work spans the entire verification lifecycle from test planning till the sign-off stage. And as a mentor with experience in both block level and full IP level testing, I'm honored to share the spotlight with Ignacio, and I'm excited to share how these methodologies ensure the reliability of modern digital design systems.
Thank you, Hassan. Before going back to you, I would like to cover the roadmap for today's webinar. We will start with the why, what makes verification essential, despite being time-consuming and difficult. And then we will explore how verification actually works, walk through the chip design life cycles, bust some common myths, and touch on careers on design verification. So Hassan, let me ask you something before beginning. You have been in this industry for a while now. When you look back at why you got into verification, what was it that drew you to this field?
Right. Okay, so for me, since the bachelor's, when I was in bachelor's, I was always interested in digital systems. I happened to learn subjects from some good teachers, probably. They made my interest in this field. And then I got the opportunity to start in semiconductor industry with the verification. And it's been around even more than 7 years. And uh, I'm never bored from this domain, and every day is a new challenge, new IP, new bug, new team. It's exciting field, and I do not have any plans to change any soon. Yes,
Good to know. Okay, thank you. So let's begin with today's content. Please, Hassan, the stage is yours.
sure, sure. So let's start with the existence of TV, why it exists, what is the reason, and what's the challenges that we are addressing using the DV domain. So let's start with the absolute basics. Why does the field even exist? This slide lays out the basic idea why the existence of these is important. First, manufacturing is astronomically expensive. Down the webinar, we'll understand what are the challenges when you send your design to the fab for the manufacturing. And before that, you have to verify each and everything because you want to save the cost at the fabrication level. If you fabricate something wrong and you found the bug and post silicon stage, which is once you have your board from the fabrication lab and you found some bug that could be fixed at the simulation level, it will cost thousands, even millions or billions, depends upon the design complexity. It will cost so many dollars. So you have to repeat the whole cycle again. So the manufacturing is astronomically expensive. A single mask set for a modern chip can cost millions of dollars. As the design are getting complex and complex, the verification and manufacturing both stages are getting more complex and expensive. And you never want to go through the complete process once the chip is fabricated. So you have to verify each and every possible scenario in the simulation cycle. And then RTL is easy to debug. So once you are in the simulation or pre-silicon level, the RTL is easy to debug. You are able to write, you are able to observe the RTL using the waveform. Once you have the board, then you do not have the source code with you, you have the actual fabricated chip. So RTL is easy to debug in the pre-silicon stages. And you can use methodologies of the verification to verify the functionality of RTL more exhaustively. And next is earlier is always better. As I mentioned, as a verification engineer, we have only one goal. We have to verify, we have to find all possible bugs in the pre-silicon stage. And that's the early stage, then the fabrication level. So you do not want to see any bug in the post-silicon stage. Design changes constantly. So new features, RTL tweaks for synthesis and timing. So once you have developed the initial RTL design, you move to the next phase, that is the physical design. And there you do the place and route. You actually design how your chip will be look, which module will be placed where. You do those things, and then you develop the netlist. And during this process, PD, sometimes it's very frequent actually. The design has to update accordingly. So somehow the performance or the area are not meeting. So the RTL engineers, they have to revise the source code. And every time when there is a change in RTL code, the verification engineers have to verify all the test cases again. So design changing constantly, therefore we need verification in the complete process. Yep. Next is, as I mentioned, verification is required for the whole cycle. So next, we'll observe the challenges of the verification. Why do we need verification? We know how what type of verification and how advanced verification do we need with the modern chips. So in this slide, this leads us to the fundamental problem of our profession, the scale problem. That is, if your design is scaling, if your design is getting complex, if your design is getting bigger, you have to verify. The verification challenges grows in proportion. So verification is at its core. And the design space is too big nowadays that it's very expensive and it's very time taking to cover the complete design for one team. Look at this example. So it's an example verifying a simple 32-bit multiplication, and it has mentioned that you might take up to century to cover all the scenarios on this 32-bit multiplier. And we do not have so much time to verify and to fabricate one chip that is just a 32-bit multiplier. That's very common in nowadays. So you have to come up with advanced methodologies to test your chip way before and with so much confidence that you can send your design to the fab for the fabrication. So our job as verification engineer is not to prove a design is perfect, because design is too complex and too big, but to reduce the risk of a bug to an acceptable level using smarter techniques. So as a verification engineers, we always try to exercise the complete design uh, with intelligent techniques in verification that we'll go through in next slides. But we cannot cover the complete design with all possible input values. It depends how much complex the design is. For simple designs, we can, yes, but for the complex design and for the large problems, for the large designs, we can't spend. So we have to come up with the technical, intelligent verification methodologies to verify smartly. So another example is the transistor complexity. So in the modern design, we have billions of transistors, and in the early stages, you can see in the earlier CPUs from the Intel back in 1900s, the number of transistors were less on the board, so less verification were required at that time. But now more transistors, more complex designs, and more challenge for the verification engineers. And you can see uh, in, in just a few years, we have explored the chip with billions of transistors. So, and you can imagine the complex designs like AI accelerators, which have billions of transistors, and each transistor is a test case for the verification team. So it's mathematically impossible to verify each transistor or each scenario on the design. That's why verification methodology had to evolve from test everything to prove correctness strategically. So we have now we have smart verification methodologies that we use to verify such complex designs in reasonable time with high confidence. So in this slide, we can see the delta in the verification effort and the verification cost. You can see in the initial stages in 1900s, when there were relatively less complex designs in the market, so no verification team was required for some of the projects. Even the design engineers, while designing, they verify the design themselves with the basic test cases. But as the designs are getting complex and the number of transistors are growing per chip, as mentioned by the Moore's law, the verification has become the main part of the design chip cycle. So for years, people assumed verification would naturally scale with the design tools, but the reality is not this. Verification cost has grown faster than the design cost. So now it's even more than 50% of the design expense and the design cycle time goes to the verification team. Because as system becomes more integrated, the interaction between components multiply. A CPU might be testable in isolation, but the CPU surrounded by cache, the memory controllers, and peripherals creates an explosion of possible states. So we can test each and every case. The industry now spends more on verification than on design for the complex chips. That's not a problem. It's a recognition of where the real work lies. So the verification cost is very high. It's very comparable nowadays. So moving forward, verification has become the critical path for both type of projects, for ASIC and for FPGA projects. Here we have some information. The average verification takes more than 50% for the ASIC projects, and same around 50% for the FPGA projects. Because finding bugs in deeply integrated systems is generally hard. A simple bug is in a module might take an hour to find, but when you are debugging on SoC level or full chip level, it might take days or weeks to root cause the actual bug. Here's the important part. This investment is rational. Catching issue early saves orders of magnitude more time later. So verification teams are required from the very start of the project, because if we skip any bug in the pre-silicon stage and we found that bug in the later stage after the post-silicon on our board, on our actual board, and we found something buggy while doing the testing with the oscilloscope, it would cost so much dollars and so much time, because you have to repeat the complete cycle again. You have to update the design accordingly. You have to do the PD again, and then you have to do the verification. You have to run all the test cases again to make sure that the bug is fixed and it's gone. So the verification at the very start is required from the very start. And question, I have a question. Now show these numbers on these slides always surprise people. So verification taking over half of the project time, more than 50% or even 60%. In your experience, does that actually match, or it actually worse?
I think actually 50 or 60% is conservative. I have seen projects where verification consume 70% of the time or more. And the tricky part is that verification is not linear. So maybe you think you
Mm-hmm.
are done, then you find a bug that forces the re-verification, as you mentioned, of the whole chip. And you can see that in the schedules. Like verification might take even more time than 60%.
Yep. And one thing that you might also have observed from the fresh engineers, that they underestimate the planning time. So they think verification starts when the RTL is ready, but the good verification engineers, they know that from the architecture evolvement, the verification has been started.
hmm Yeah, exactly. That's a key point. The earlier you start asking how will we test this, is the better. So
Yeah.
maybe we can come back to this concept when we talk about verification carriers.
Yes. So next is some real bugs happen and their consequences. So there are few examples, but we have so many other examples as well. If the verification team misses something, what could have happened? So we have combined three examples, and they are available online. You can search. So in the first example, Threat 25 radiation machine. So it cost us human lives. So something was missed at the verification, and it was exposed while actual not testing, but while actually using the machine with the patients, and some of the patients got killed, and we cost human lives actually, and not one, at least six were reported. And again, another example, the Mars Climate Orbiter, the famous one. So shuttle that was launched towards Mars, one minute case was missed in the testing, and it got explored in the actual performance, and the complete project explored, and it cost millions of dollars, and it's also reported. And again, another example is the DC motor crash. So in the train, something was not very well tested, got crashed, and again, it cost the human lives. So these examples are the proof that why verification is important and how much verification is important. So you have to test each and every scenario in which your design will be exercised. So as a verification engineer, we have to be aware of all the possible scenarios in which our design could be placed, and we have to test it in pre-silicon, post-silicon, but before delivering it to the client. Moving forward, so another example. the famous one, the bug that was reported in the Intel Pentium CPU, and many of us might have used these CPUs as well. So hardware error in the floating point unit caused inaccurate floating point division results in the CPU, and it was caught by a professor while doing some experiments. And the company had to fix this bug, but this was shipped out and shipped out product. So they collected the CPUs, those were delivered, they collected back, and then they fixed the issue, and then they delivered the correct items. Another example is the FWF bug. An invalid operand in the CPU was not tested, and it caused the processor halted during processing. The only solution was to reboot the CPU, and whenever this instruction happen again, the CPU stucks. So these are the examples which are made public and shows the importance of verification, why and from where. From the very start, it is required till the very end of the project. So these are the examples which are publicly available, but there are some other examples as well which are not publicly available, or some secret examples. So we have seen why verification exists and what's the importance of verification. So next comes the design cycle, where verification fits in the chip design cycle. So in this slide, we have mentioned all the basic major steps in the chip design cycle, starting from the requirement, followed by specification, architecture, the designing, RTL designing, then verification, synthesis, physical design, manufacturing. So they are mentioned in the index. In the following slides, we'll see how verification fits in this design cycle. So moving forward, these stages are divided in pre-silicon and post-silicon stages. So in pre-silicon, you have the planning, then front end and the back end. So in planning stage, the architect engineers, they collect the requirements from the client, what needs to be developed, for what purpose the chip is going to be developed. So in architecture, they develop a high-level architect using some computer architecture. It could be RISC-V, ARM, or any specific custom architecture. They develop the architecture of the chip, and from the architecture, the design engineers, they develop the micro architect. So they read the architect and they develop the RTL, the actual source code. And they develop the micro arch document as well. And from the micro arch document, they develop the RTL source code. That's the planning phase. And then comes the front end phase. In the front end, you develop the understanding of the design, you code, and then you compile your code, and then you simulate using simulators, and you verify. And the front end, it's, you can see in the diagram, it's to and fro movement. So if something is found, if some bug is found in verification, then they report back to the RTL team to fix it. And if sometimes there is a issue with the architect, the design team or the verification team can challenge the micro arch document or the architect decisions. Then comes the backend. So in backend phase, we do the physical design. So once the RTL is designed and it's tested, you do the synthesis, you do place and route, and then you also do the timing violations, timing verification. And next, about the post silicon. So once you have completed the pre-silicon stages and you have the netlist with you, you send that to the fab for the manufacturing. And in the fab, they have their own decent and complex procedure to make a chip from ingot and then make it to the customer. So in this stage, they have they got the silicon ingot. They have their complex procedure of 20 to 40 processing steps. It's very complicated. They make the wafers from the silicon wafers from the silicon ingot, and then they dice it, they package, and then they finally test the chip. And once all the tests are passed, they ship the product back to the company. And each step introduces potential failure modes. Post-silicon validation confirms the chip meets specifications in the real world. So once the chip is past post-silicon stage, you have the actual board, you run your applications, your OS on the chip, and then you make sure that the chip is actually working in the real world scenarios. So the main point is where the verification fits in this life cycle. So this diagram ties it all together. Verification spans from specifications through tape out. Validation and manufacturing test begins after verification, after fabrication. So the key insight: groundwork for post-silicon testing is laid pre-silicon. Test bench, reference models, debug tools, all should be designed for reuse. When silicon returns, you do not want to start from scratch. It means the test bench that you developed in the pre-silicon stage for using X simulation, you try to make it reusable so that the same test bench could be used in the post-silicon stages as well, wherever required. So you can see from the diagram that the verification starts from the very start, from the very first day. You get the specification, the architect team is developing the architecture, the design team is developing microarch from the architect document and developing the RTL actual source code. The verification team has started the verification. So verification spans from specifications through tape out. So it's the longest path, therefore it's the critical path in the chip design cycle. Next, we have some intro about all these phases. In requirement phase, the team, it's combined effort of the business unit with the engineers, so they understand the functional performance and power requirements for the client, and then they develop some documents that can be used for the engineers. And then come the specifications. In this stage, in second stage, the architect, engineers take the requirements from the business unit, and they define detailed technical specifications for the chip. They question intent, assumptions, and corner cases to eliminate ambiguity before the implementation. And architect stage, you go further into the details of the design, followed by the RTL design. So after the architect, micro architect stage, the RTL design team, they develop the source code. They start write the source code using the HDL hardware descriptive languages. And moving forward, further in the life cycle stages, we get to the PT stage where we go through the synthesis through manufacturing. So in synthesis, we convert the RTL code to gate level netlist using EDA tools, and we confirm synthesis preserves functional equivalence and does not introduce timing issues. And in the physical design stage, translate the gate level netlist to a physical layout and ensure that the PPA are met as required, the performance and area requirements are met. And then the manufacturing thing. So validate silicon behaves correctly. So we send the design netlist files to the fab, and then fab develops, manufacture the chip. And once that chip is developed, we validate silicon behaves correctly in real world and matches per silicon expectations. Once that is done, then we are good to ship out the chip to the market. So high level distinguishing between pre-silicon and post-silicon. In pre-silicon, Verify the design before manufacturing using simulation and formal methods. We'll go into the details of the simulation and formal as well. We catch bugs at RTL level. So we have the source code available to us and it's cheapest to fix. So we found some bug, we ask the RTL design team and then they update the source code accordingly. Challenges are complex and time-consuming simulation. So sometimes if the design is too complex, simulation might take time as well. And complete re-verification may take weeks. In the post-silicon, we test the physical chip after the fabrication, faster but far more limited. So the speed of test to run on the post-silicon chip is very fast compared to the simulation, but you have limited visibility to the design. You can't observe all the internal signals. You have board with you. You can't see the source code at this stage. And fixing a bug requires redesign plus new manufacturing cycle. That's very costly. And the challenge is recreating bugs in simulation. So if you found something buggy in the post silicon, you try to regenerate it at the simulation level so that you can pinpoint the actual bug and you report it to the design team. And this complete cycle takes time and it's complex to root cause the bug from post silicon and then to regenerate it at the simulation level. It's a bit tricky and it's technical. So the verification is not a phase. From all these examples and all this discussion, we have come to know that verification is not just one phase. It starts from the very first step till the very end, till the tape out. So it's a mindset applied continuously throughout the entire chip design lifecycle, from the first requirement to the final silicon validation. The idea of verification is a mindset, is a big culture shift for many design teams. So you might have heard that the verification team starts that work from phase X to phase Y. It's not that. So the verification teams are busy continuously throughout the project. Moving forward. So we have discussed the importance and the criticality. So here are some examples why verification is the critical path. So let's these numbers sink in. 55% for the ASIC project time goes to verification, and around 50% for the verification time goes to verification. The cost of single unit mismatch bug that wasn't caught pre-silicon cost us $327 million. That mission would have succeeded with better verification. And 103 non-defects in one processor are released. Not potential bugs, these are the reported and non-bugs that made it to customer. Each one escaped verification. So you see the verification is critical. So the key takeaways from this segment was bugs are inevitable, and customarily the cost curve is exponential. The earlier a bug is found, the cheaper and faster it is to fix. So it's always better to find the bug and simulation and fix it with the design team at the simulation level. And exhaustive testing is impossible with the complex designs. We need smart methodologies, uh, constraint, random and formal and coverage-driven verification techniques to verify the design. Verification owns the critical path more than 50% of the project time, and the proportional cost goes to verification. And pre-silicon investment pays off. If the pre-silicon verification is decent enough, you will be confident enough with your post-silicon product. But if you found something buggy in the post-silicon stage, you get doubtful about the pre-silicon stage as well. So you repeat the pre-silicon phase again. So
Okay,
these,
thank you, Hassan. Let me ask you something after this first section.
Mhm.
What's something or one thing that you would want someone new to verification to walk away with? Which concept for you is essential regarding this?
Right. So till now we have discussed the high level basic reasons why DV exists and what challenges do we face. So for me, it's that verification isn't about being perfect. It's about reducing risk intelligently. So the design team cannot for me, I am very shy to say this statement to my project manager that this design is bug free 100%. So we always say that we are confident enough, we have tested this case, and we are confident enough that this chip would work as intended in the real world. So you'll never catch every bug. The skill is knowing where to focus uh, more, and where you focus limited to catch the ones that really matter. So I have the same question from you.
I think that some of the critical takeaway here is that um, is regarding the cost curve. So
Mhm.
if you caught a bug early in the design cycle, it might cost pennies. But if you caught the same bug later, it could cost millions. So that thought should shape every decision in the chip design cycle. So we need to really think on when verification starts at the beginning of the planning, how
Mhm.
verification will be done. Um, and it's not just about testing everything. It's about testing the right things at the right time, let's say.
Yep, that's actually a great lead uh, to our next section on how verification actually works. So let's get to it.
Okay, thank you, Hassan. We so far we have established why verification exists, why it is important. Now let's move on to how do we actually go into verifying a design. In this section, we will explore verification levels, test benches architectures, strategies regarding checking and stimulus, and some industry standard methodologies for verification. So verification happens at multiple levels, from individual logic blocks to full system integration. Why do we have so many levels? Because each level focus on a different thing. Unit level tests find local bugs cheaply, while system levels verification find integration bugs that unit testing might miss. So the rule here is to catch bugs at the lowest level possible. A bug found in unit level might cost just hours to fix, and the same bug found at system level could cost like hours, days, or weeks to fix. So pre-silicon verification is structured as a hierarchy. We begin with unit testing. This is basic, simple, and fast, and is often done by the designer. This is a good level for formal property verification. We will begin into formal a few slides later. At this level, we target individual modules like an ALU or a cache, where we have maximum controllability. At this level, we catch initial bugs. We might have a dedicated environment per each module. In the next level, which is the block level, we test multiple integrated modules like a DRAM controller or a core processor. We target inter-block protocols and connections. We have less controllability than at unit level. And most of the bugs are found here at this level. Then we move on to core or subsystem level, where we test for connections and transactions across integrated blocks. And then we move to system or full chip integration level. Here we have the lowest controllability and the lowest visibility. And we target integration defects and software-hardware interaction. At this level, we usually use techniques on FPGA or emulation. We test for interconnections, integration, transaction interactions. And as we move up into each level, the complexity increases and the visibility and controllability decreases. So we need more sophisticated test benches infrastructures as we go up into the levels of verification. We need to invest a lot at unit level, where finding the bugs is cheapest, and scale up as integration is validated. Let's dig into these levels a little more. So as we mentioned, in unit level, we test individual components in isolation, a cache, an ALU, a register file, each one with its own test bench. We focus on boundary conditions and edge cases. For example, if an ALU handles an overflow correctly, or if a cache evicts a line when it's full. Moving up a block level, we test integrated units that form a coherent block. For example, a cache controller managing the cache hierarchy, a processor with all of its units. And here we focus on protocol adherence. For example, if blocks communicates to each other correctly. Most of the bugs are caught here because the controllability is maximum. We can apply any stimulus, force any state, inject anything that we want into our blocks. And later levels might lose this fine grain control. At subsystem level, we verify the interfaces between blocks. For example, at this level, we might verify a memory subsystem with cores, caches, the DMA, and the main memory, or a GPU with its rendering engine, the shader core, the memory interface. Here we focus on interblock communication. Do they handshake correctly? Does the data flow as expected, etc. And then moving on to system level, we test the full chip integration, end-to-end testing. For example, a processor plus the memory, plus the peripherals, the USB, Bluetooth, the display controller. And here the focus is shift to real-world scenarios and corner case interactions. Here we run actual software workloads into our design. The assumption at this level is that lower levels are already well validated. So, for example, a system level testing is not meant to find bugs in an ALU. So it's for finding integration bugs that only appear when everything is running together. And finding a bug in an ALU, for example, it means that our block level verification or unit level verification was not completely done, and it might have a higher cost to find it here because we need to isolate the bug and test everything again from the block or unit level and up. So, which verification level should we choose when verifying a design? The core principle is to choose the lowest level that completely covers a feature. Lower levels are usually offer easier simulation, are faster. Detecting the bug at the lower level is faster. We have better observability. And debugging at unit level might take hours, while the same bug at system level might take weeks. When should we go to higher levels? When there are complex cross-unit interactions that require system-level testing. At higher levels, the isolation of the bug increases, the cost also increases, and could be a risk in the schedule. So controllability and observability are fundamental to effective verification at any of the levels, and we should optimize our test benches or our strategies for both, for controllability and for observability. Let's compare lower level versus higher level verification. As we mentioned, lower levels give us full control and visibility. We can force any signal, see any wire, and debug in hours. And here is where we catch most of the bugs, and we can fix them cheaply. We just find the bug, find the cause easily, and tell the designer there's something that needs to be changed that causing this bug, and the designer changes the RTL, and we can test again. At higher level, we sacrifice that visibility, but it's essential for catching integration bugs that only appears when blocks interact. The strategy here is simple. Verify at the lowest level that completely covers what we are testing. And then we scale up methodically. When we don't have to move to system level until the blocks beneath are solid. Otherwise, we might face a failure and it becomes a guessing game on where the bug might be. So how do we proceed into verifying a design from lower levels to upper levels? Here is where test benches are built. So what is a test bench? It's a custom test harness for our DUT, or design under test, where we apply stimulus to that design and check the outputs of the design. Ideally, these checks are done against a reference model or at least in an automated way. Let's dig into how do we drive stimulus into the design. And this depends on what we can see about the design. We have three main driving strategies for stimulating the design. We have black box strategies, white box strategies, or gray box strategies. In a black box strategy, we don't have internal visibility on the design that we are testing. We only know the specifications and the input and output interfaces. So we use these specifications to randomize testing to maximize the scenario's coverage. We only test through inputs and outputs. We don't know anything about the inner signals of the design. In a white box strategy, we have the opposite case. We have full internal access to the design. We can target our stimulus to hit internal states, specific signals, corner cases, and this is often combined with formal verification for exhaustive coverage. Then a gray box strategy is a mix of both, where we might have partial visibility into our design. For example, we might see some internal signals, but other parts of the design might be encrypted. So this combines external stimulus with assertions at observable points. So each of these strategies has its place. We use black box for maximum stimulus variety, white box for targeted coverage, or a gray box for constrained visibility situations. In most cases, in real world, what we face is a gray box scenario, which mixes both white box and black box. Let's see this with an example. A 4-bit ALU. If we face verifying this DUT with a black box strategy, we should apply all input combinations for every operation, and we compare the outputs to the expected results. This is very simple. We can do it thoroughly for small designs, but it doesn't scale. If we apply a white box strategy for this ALU, we can target internal corner cases. For example, an overflow detection. We can check the carry flag propagation. So we need internal visibility to verify these test cases correctly. And a gray box strategy combines external testing with partial observability. Maybe we can see a status register, but not the internal carry chains of the ALU. So we monitor whatever we can see. And we might need to infer the internal behavior of the design. On the other side, we have checking strategies for checking the responses of the design. We can have different types or levels of checkers. We can have input and output checkers, which detect output mismatches. Here we need to check values at all times, both expected values and unexpected values, and must be abstract and design independent. We should never reuse the RTL code as checkers because in this case we could duplicate the bugs. Design context checkers understand the big picture interactions. We need to understand how each of the blocks interact with each other and with other checkers. For microarchitectural checkers, we should be aware of the implementation of the design. We can check internal states, data structures, invalid data detection, or fine control timing scenarios. And architectural checkers are implementation independent and are related to protocol compliance checking. For example, when we are trying to check a communication protocol or an interface handshaking or data integrity requirements. For all of these checkers, specifications are essential. So the checkers are only as good as our understanding of what correct actually means. Let's also see this kind of checkers with the same ALU example. In this table, we can see different kind of checkers for the same DUT. For example, an input and output checker for the ALU could be verifying the result of an operation. This is simple and it's essential. Or, for example, we should check that there's no output when there's no operation. So the output should be idle. A design context checker could check that the output is consistent across operation sequences, that the previous result persists correctly until a new operation comes. A microarchitectural check could be an overflow detection or the carry signal, as we mentioned before. This is implementation specific. Or also an invalid opcode handling. We should check that there's a correct response with an unsupported operation. An architectural check, for example, could be the compliance of the handshaking signals of the module according to the specification and the defined rules of that handshaking. So every checker targets different failure modes, and together they all provide a comprehensive validation. Hassan, let me ask you something about this. For example, I heard from junior engineers that asks all the time, how do I know if or what checkers to write? How do I know what can go wrong? Does this happen to you anytime? You're muted, Hassan. Sorry.
Right, Shaman. No, sorry. So
Okay.
yeah, that's a common question, and it's the hardest part of our job as verification engineers? The answer is the thinking, not the coding. My advice is always start with the specification. Every line in the spec is a test case that verification team has to test, and it's either an input or an output or a rule that you will follow to write the checker and your reference model. Each of those is a potential checker, and then think like a adversary. If I want to break the design, how would I do it?
Yeah, you are right. I also tell the engineers to look at the design and to try to think about the designers. What did they try to do? What they assumed? And on those assumptions is where we usually find
Mhm.
bugs. Um, if the designer, for example, assumed that two signals would never be high at the same time, that's exactly what you should test. If those two signals are high, or what happens if they are not high at the same time.
Yep, you're right. And that's where the white box testing is helpful. So in white box, you can see the assumptions in the RTL, what assumptions have been used by design team, and you can challenge them using your checkers and stimulus in the
Mhm.
test case.
Thanks, Hassan. Moving forward, we have also different styles for checking strategies. We might have golden vectors, which are pre-calculated input-output pairs. This is simple and effective for well-defined functions, um, but these are limited to pre-computed scenarios. We cannot test every possible scenario with golden vectors. On the opposite side, we can have a golden reference model, which is higher abstraction model that mimics the DUT behavior, and it generates the expected results automatically from the same stimulus that the DUT is receiving. Um, this strategy is more flexible than golden vectors, but also requires developing and maintaining the reference model. And also we have transaction-based strategies where we abstract the low-level signals into transactions. For example, a read, a write, a reset operation is sent to both the DUT and the scoreboard, and then is later converted to the signals at the interface level. When the scoreboard receives these same transactions, it generates the expected results. And this is most scalable for complex protocols. So we need to choose the correct style and strategy based on the design complexity and the verification requirements. So moving forward into how a test bench is built and layered. So why do we have layers in a test bench? Because separation of functions is crucial. So each component in the test bench has its own job. For example, a change in the stimulus generation shouldn't affect how checking is done. Um, and we can reuse existing components for different scenarios. So this layer architecture enables the reusing of the test bench across multiple projects and multiple teams. Normally, in a layer test bench, we have the test, which includes a generator, an agent, and a driver, which includes the whole environment containing the generating part of the stimulus and the checking part of the results. And also a scoreboard that might or might not be present for computing the expected results. The environment also should include or might include assertions for checking of protocol violations in line with the DUT, and a functional coverage model to track verification towards completeness. We will see more about this layer test bench later in the presentation and why this is so important. This brings us to one of the most powerful combination in dynamic verification, directed versus constrained random stimulus. So we might have two kind of tests, direct tests versus constrained random tests. A direct test finds the bugs that you expect. So you write a test for a specific feature. Meanwhile, a constrained random test finds the bugs that you have never anticipated. So you write a test that says generate 1,000 random but legal instructions, for example, for my CPU. And this might hit a corner case that you never thought to write in a directed test. So for a complete verification, we need to develop both kind of tests. Usually we begin with directed tests to target specific features that we understand from the specifications. And then we might trigger the generation of random stimulus in order to find the bugs that we never thought of. Let's dig into different verification methodologies. Let's begin with pre-silicon verification methodologies. First, thinking about the right test bench, which depends on the context. So the test bench architecture might run simultaneously for the same design under different contexts. For example, we might run our test bench in simulation, which is a software-based methodology, and it's cycle accurate. And it's usually the most common flow for unit and block level verification. It's a methodology that's flexible, it's debuggable, but it is slow. It is slow. So running in simulation might take more time than running the same test bench in another architecture, for example, in FPGA. FPGA or emulation is where we map our design into an FPGA or into an emulation platform that run at near real-time speed. So this enables system-level testing and software bring-up, and it's a lot faster than simulation, but this is harder to debug. Here we lose visibility on the inner signals of the design. And another methodology could be formal property checking, which it tests specific properties in a mathematical way. It's ideal for control logic and protocols, but not for data paths. Here we don't need test cases, and we prove the correctness for all of the inputs. So each of these methodologies serves a different purpose. Simulation is for depth, formal for proofs, and emulation is for speed. And here we can visualize the coverage area for each of these methodologies. In simulation, we spot coverage of a design space. This is fast and flexible, but the coverage depends on the test quality. If we think of this as exploring a dark room, for example, this would be as turning on a flashlight. You only see where you are pointing at. In FPGA and emulation, we have improved coverage of the design space with near real-time execution. This enables software bring up and running long tests. If we think about it again with a dark room example, it's like turning on the lights. You see much more, but you still have blind spots. In formal verification, we exhaustively test targeted areas. It proves properties mathematically. It's like having X-ray vision of the darkroom, but for only for specific features. It's complete certainty, but only under some scope. So none of these approaches win, and an effective verification should implement all of these. It should combine these three approaches. Let's begin with simulation-based verification. Here, we use a software tool to simulate the chip behavior. A stimulus is applied to the RTL inputs. The outputs are captured and checked. Here we catch bugs before silicon fabrication, and the test scenarios that we write or produce try to reproduce the real hardware. And this is the foundation of most of the verification flows. For example, a functional simulation of a matrix multiplier. We can apply input matrices, verify that the output matches the expected results, and we can run thousands of test cases overnight. But again, the simulation's limitation is speed. Fast simulators can run at kilohertz but it's millions of times lower than real hardware. So long tests requires other methodology like emulation or FPGA prototyping. Regarding simulation, we here come to the concept of system Verilog and UVM. UVM is a methodology, a standard methodology for building a layer test bench as the one we have seen before. UVM has been a standard for over a decade, and it's built in system Verilog. It combines HDL constructs with verification-specific features, with system Verilog assertions, with constraint randomization, object-oriented programming, and coverage-driven verification. So UVM gives a blueprint for building the components of that layered architecture test bench that we saw. Agents, drivers, monitors, scoreboards. It is heavily focused on reusability and in constraint random verification. For example, if you build a UVM environment for a USB controller, you can reuse the same environment across multiple projects. So the value of UVM is its scalability and its reusability. And once we learn UVM, we might be able to work in any kind of UVM test bench. This is the value of using a standard verification methodology. So summarizing this part, what should we do? We should verify at every level, but trying to think where to apply each level of verification. And keep in mind that catching bugs earlier is the cheapest. We should choose our test bench strategy deliberately, whether we have to apply a black, white, or gray box strategy based on the visibility and the coverage needs. We should balance directed tests with constrained random stimulus. Constrained random is for catching unexpected bugs, while later applying directed tests for coverage closure. And we should layer our test bench, separating each functionality of the components in order to be able to reuse them, scale them, and use a consistent methodology across all of our verification efforts. Another methodology that is gaining a lot of usage nowadays is CocoTV, which it's easier to learn than UVM. UVM has a steep learning curve. It's very complex, so this has led to this interesting alternative. CocoTV is open source, is a Python-based framework, and it lets you write test benches in Python, which is much more easier to learn than System Verilog and UVM. And one advantage of CocoTV is that it integrates really simply with software development tools like continuous integration and continuous development pipelines. So we can write our test benches in Python and interface these test benches with the simulators via a very low procedural interface for interfacing with C or with the foreign language interface that these simulators provide. It's really beginner friendly. It's widely known. And one of its main advantages is that it is free and open source, so we don't have to pay for EDA licenses. So CocoTV democratizes verification. It's a really powerful tool for students, startups, for open source projects, and we can verify designs without a big budget for paying for EDA tools. Here we can see a trade-off between UVM and CocoTV. UVM offers maximum reusability and standardization, but with high complexity, and is often tied to expensive ADA simulators, while CocoTV offers ease of use and software integration, but its reusability depends mostly on the discipline of the user. It doesn't provide a standard methodology. Regarding the cost, well, UVM requires expensive licenses, while CocoTV is free and open source. So this is really significant for small teams. We need to choose which methodology to apply based on the context. UVM is normally applied for industry standard projects with reusability requirements, and CocoTV is for agile teams, for education, for open source as well. Another verification methodology is formal verification, as we mentioned. Formal verification is instead of simulating with test vectors, it uses mathematical proofs to exhaustively verify a property of the design. For example, if you have a property that says when the bus is in state X, signal Y must be always true. So formal can prove that this property holds for every possible input sequence. It doesn't just sample the design space, but instead it covers the whole thing. This is critical, or this is a game changer for safety critical logic, for example, the airbag controller of a car. There are three main types of formal verification. Property-based verification, which checks the design behavior against formal specifications. Here we write assertions, and the tool proves that these assertions proves true for all of the inputs. Another type of formal verification is equivalence checking. This proves that two representations of the design are functionally identical. For example, the RTL versus the netlist that we get after synthesis. It's essential for checking that the tools didn't introduce any bugs. And another type of formal verification is model checking, where we exhaustively explore all of the reachable states in FSMs, proving that properties hold everywhere and not just where the tests reach. So in formal, we doesn't need test cases. It provides correctness exhaustively within its scope. It doesn't replace simulation, but it complements it for high assurance of properties where exhaustive proof is essential. The downside is that it suffers from state space explosion. It's brilliant for small and complex control logic, but it chokes on large data paths. Formal tools excel on bounded arithmetic blocks, but struggle with full processor cores, for example. So we need to apply formal selectively. We need to target properties, protocols, control logic, where exhaustive proof is essential. And we need to pair this with simulation for broader coverage. Again, these tools don't replace simulation, but it complements simulation for high assurance properties. Here we can compare simulation versus formal. Simulation is easier to implement and to understand than formal. And formal requires mathematical and formal methods expertise. Regarding coverage, simulation is limited to test cases, while formal exhaustively tests all possible scenarios within the scope. Regarding the compute cost, simulation is cheaper per run, but we might need many test cases. And formal, it's expensive, especially for large designs, because it needs a lot of computing power. Regarding speed, simulation is manageable for small designs, and formal is slower due to full state space analysis. And the best use of these tools, simulation is general for functional testing, and formal is better for safety critical or protocol critical components. So we need to use formal for critical properties requiring absolute correctness, and simulation for broad functional coverage. And finally, we have another verification approach, which is FPGA based. Here we take our RTL design and map it into an FPGA, which runs at near real-time speeds, which is millions of times faster than RTL simulation. For example, you can boot a whole operating system on a CPU before building the actual chip. The downside of this is that mapping this RTL into the FPGA might take a lot of time, but we might compress hours of simulation time on an FPGA. We can apply real-world stimulus, like connect our actual sensors, displays, peripherals, for authentic interaction of these peripherals with the design and testing them. And we can prototype our design earlier to validate complex interactions before fabricating the chip. The trade-off of FPGA verification, well, its debug visibility is low. It's hard to see what is happening inside the FPGA. You often need to have special logic just to have a peek of the internal signals of the design. Adapting the RTL designs for FPGA requires significant time and tool expertise, especially time enclosure for FPGA. And the FPGA architecture usually differs from the ASIC targets. There might be timing, power, and routing differences that might cause behavior mismatches versus the actual chip. So FPGA is not perfect, but it's really powerful. And we need to use it, understanding its limitations. Comparing FPGA versus simulation, well, FPGA speed is almost near to real time. It's very fast. Simulation is slower and depends on the compute resources. With the FPGA, we can interact with the peripherals, with actual peripherals or sensors, and simulation is limited to virtual or model scenarios. Debugging on FPGA is really difficult because we have little visibility of the design. Meanwhile, in simulation, we have visibility of all the internal signals of the design. The accuracy in FPGA, it might differ from the actual chip, while in simulation, the simulation matches the intended chip behavior closely. So FPGA is better for real-time performance and hardware integration tests, and simulation is better for functional corner cases and early bug detection. So no single methods wins. We need to combine them all. Each one occupies a distinct point in speed, accuracy, and cost, right? Simulation is flexible, provides flexible debugging and broad coverage early in the design cycle. Is best for finding bugs, but not for running long tests. FPGA is for running at real speed and for integration of the design. It's best for system validation and software to bring up. And formal is best for safety critical scenarios or for protocol critical logic. An effective verification program should combine all of these three methodologies across different stages in the design cycle. Summarizing this, a winning strategy uses all of these methods. We need to balance the verification approach to use each of these methods where they should be applied and where they deliver the most value. Together, they are stronger than any of them alone, and a strategic combination covers the weakness of each of these with the strengths of the others. So we need to apply them where they are the most where they deliver the most value and combine the three of them. So moving on into how do we measure the verification progress. We have seen all of these three methods running, but how do we know if we are making progress towards finding bugs and completing our verification? This is where a really big question comes up. When or how do we know when we are done verifying? We can run simulations until we get bored. So we need metrics to see when we are done verifying. The progress in verification is not linear. In the first stage of the design, we might find bugs really fast, but then the existing tests might not find any more bugs. So this inflection point is critical. So here is when we need to shift from directed testing to metric-driven verification and enable coverage collection. In this way, we start seeing coverage holes, and we need to start writing tests for uncoverage areas. Here we can see, or we might expect the bug rate to increase again, meaning that our approach, our verification methodology is working. We start exercising scenarios that were not previously hit, and we start finding new bugs. This metric-driven approach unlocks deeper design validation, and it enables measurable risk reduction. One of the metric that we use for verifying are assertions, which are little executable specs that are embedded in the code, and they constantly monitor the design. Saying, for example, if we are in this state, the design must never do that. So they are really great for catching these kind of things and bugs when they happen. Um, they verify that the design obeys some specification rules, and they are triggered when the rule is exercised, confirming that that scenario was reached. And they fail immediately if the rule is violated, point link directly to what went wrong. Um, for example, an assertion might say, if a valid is high, then the ready must eventually go high, confirming that the handshake protocol is actually working. So whenever the valid signal is high, the assertion is triggered, and it should check that the ready signal should go high. This approach helps catching bugs earlier before they propagate into complex failure scenarios. An assertion failure is really easy to debug, while if this is not implemented, this might produce an scenario that's really difficult to track the cause of the failure. And another metric that is essential for metric-driven verification is coverage. We have two types of coverage. Code coverage, which is automatically gathered by the tool that we are using, measures which lines of the RTL code, which branches, which state machines were exercised, and it answers to the question if the simulation actually ran all of the code that we wrote for the DUT. But a line of the code could be executed with the wrong data, so code coverage alone is not enough. This is why we need functional coverage, which is the other type of coverage. Functional coverage is user-defined, and as verification engineers, we need to write cover groups that capture interesting scenarios from the specifications. For example, did we see a read after write to the same address, or did a FIFO ever go full? Functional coverage answers if we exercise all the functionality described in the specifications. So this flow is iterative. We write a test plan, we run simulations, we look at coverage, we see the gaps, and then we write new tests or adjust the constraints to fill those gaps. And we need to repeat this until we have met our coverage goals and all of our assertions are clean. So that's when we are free to say that we are ready for taping out. So that would conclude with my part of this presentation. Please, Hassan, you can go on.
Next comes some common verification myths. So before we wrap up, let's debunk some of these myths. Understanding what verification cannot do is important as mastering what it can. And these myths persist because they are comforting. If we just verify enough, I will find all bugs. Reality is even harder and more interesting, and we'll observe from these myths. So the first myth is verification proves the design is bug-free. And I have already mentioned this at the very start of our webinar. Reality is a bit different. So the reality is verification reduces the risk. It cannot eliminate it. Unexercised corner cases must still exist. So if you develop some test plan for some design and you miss some case in your test plan, so you are not going to generate the stimulus for the test case, and it will that part of the design would be untested, and you cannot say about the bug frequency in that part. So think of verification like exploring a dark cave. So you can map every tunnel you find, but you cannot prove there are no undiscovered passages. New bugs may lurk in states you never reached. This isn't defeatism, it's intellectual honesty, actually. Acknowledging limitations make us better verifiers. We focus on risk reduction, not chasing the impossible dream of perfection. So verification is as good as your test plans. The planning phase is as important as rest of the verification itself. So to the next myth, 100% coverage. So we have discussed the coverage and types of coverage already. So there's a myth. 100% coverage means the design is correct. Again, it's a myth, and the reality is a bit different. Coverage shows what you tested, not what you missed. Gaps in the test plan are invisible to coverage tools. Again, if develop some test plan and you miss something, and from that test plan you develop the coverage plan as well, and you miss something in the coverage plan as well, and you forget to write the functional cover point or even one bin for that functional coverage, this will be untested, and we cannot say whether the bug resides there or not, because we actually do not know. We haven't tested that part of the design. So imagine testing a car by driving it in circle. You achieve 100% coverage of driving in circle scenarios. Does that prove the car works for highway merging, parallel parking, or off-roading? Can't say unless we try all these test cases with the car. So coverage metric only measure against your test plan. If your plan misses important scenarios, coverage won't save you. The 100% number is meaningless if you are measuring the wrong thing. And moving to the next myth, here comes the next myth. The constrained random verification will eventually find all bugs. So again, it's a myth. And the reality is constrained random explores probability space. So if you are trying to verify a very complex design with the formal mechanism, formal methodology, you will have to wait for so many years. You have to wait forever, because sometimes the designs are not designs do not converge. These state space explores and put so many possible input scenarios to test, and rare cases may never be hit. So think of a 62-bit adder. So for this, we have so many possible input combinations, and the constant random verification might run for years without hitting a specific rare corner case. The probability space is just too large. And CRV is powerful but not magical. It finds bugs you never anticipated, but it won't find every bug. Direct testing and formal methodologies close the gap CRV leaves. So the to address this myth, we have to combine other methodologies like directed testing as well. So moving to the next myth, verification is mostly a writing test. So it's the most common myth, but it's not in reality. Most effort is thinking what can go wrong, what matters most, what is the real risk. So as verification engineers, our job is not just to write the test. Our job is not just to write the coverage property or assertion or the cover point, but as verification engineers, we have to think what needs to be tested, and what needs to be tested from VM, and what needs to be tested from formal, and what needs to be tested at emulation. So most effort is about thinking. typing test code is just mechanical thing, and with efficient AI tools, that thing is already being taken care of. The hard part is deciding what to test, analyzing specifications from the architect, documents from the microarch, and challenging each line of the code using your test case is the real job. Great verifiers spend more time about thinking than coding. They ask, what if constantly? So, what if this line does not work? What if that condition does not verifies? They imagine failure modes designers never considered. So they always challenge the assumptions made by the design engineers, and they never use the design piece of code in the reference model, because they can, as Ignacio mentioned, they can make the same assumption in the reference model, and you can avoid the actual bug. The code is just the final expression of that thinking, not the actual job. So these were some common myths we just discussed. So here, I would like to ask a question from Ignacio. Which of these myths do you see most often in practice in your team?
Um, I think that the myth regarding 100% coverage means correct. I have seen many times that people celebrate the 100% coverage and then later find a bug that they have missed. So the coverage tool measure what you did test, but not what you should have tested. So this is something most engineers need to understand, I think.
Yep.
How about you? What's the myth that you often see in practice?
Right. So uh, when we are developing test bench using Moscow Melee and UVM, so we use CRV methodologies to generate the sequences. So CRV, sometimes the engineers rely 100% on the CRV, the constraint random verification methodology. But people think constraint random is magic, but the constraints themselves are assumptions. So we are using the constraints. We are actually limiting the scenarios that we can test, and if we over constrain something, then it is very probable that we miss some actual test case where the bug actually resides. So if your constraints are wrong or over constrained, you'll never generate the failing scenario. Randomization is powerful, but it's not exhaustive. So you have to take the balance between the CRV and the direct testing.
Exactly, you need both. So direct tests again to close the specific gaps that were not covered by CRV and that you discover thanks to CRV, right?
Yep.
So none of these approaches alone is enough. We need both.
Yes. So moving forward, here comes the verification as career. Uh, this leads us to the fact that verification is an amazing career. I hope that whatever we have discussed till now, and you're staying in this webinar with us, it means you are interested to some extent as well. You get to work on technology that protects lives and build uh, multi-billion-dollar products. You get a deep technical exposure to architect and protocols, and verification offers diverse career paths. As I mentioned at the very start, answering Ignacio's question, that it's been too many years and we are still getting started, and uh, we are never bored doing our verification job. So in verification, as a verification engineer, you may see the verification engineers working in three roles. These are very common. They may vary from company to company, but these are the high level roles. So at the very start of your career, you start as a DV engineer, and you start learning the verification domain. So you write test plans, you get yourself introduced with all the methodologies that we just discussed: the constraint random, the assertions, the formal verification. And some of the engineers, some of the experienced engineers, they start working as lead verification engineers. So these engineers actually own the verification plans. So they do the thinking part with the team. They own the verification plans, they develop the test plans, they develop the coverage plans, and then they make sure that these test plans and coverage plans are being executed, and the IP, the design under test, is ready to be signed off. And then they decide uh, what needs to be tested for the at the block level and what needs to be tested at the full chip level. And then some of the engineers, you will see some of the engineers working in post silicon phase, post validation or post silicon phase. So they actually bridge pre and post silicon verification techniques. They debug real hardware using pre silicon tools and models. So some dedicated tools are there in the market that are used in the post silicon phase, but we try to develop the test bench synthesizable in the pre-silicon stage, so that we will be leveraging these test benches in the post-silicon validation stage as well. So verification engineers are among the most in-demand roles in semiconductor companies. Validation is the critical path that has been proven. So it's amazing career. So moving forward, why verification is still a rewarding career. So as verification engineer, you work very close to architect team, and you uh, may challenge the architect decisions or the design decisions, uh, and you may direct the architect team to change the architecture altogether. So verification engineers work directly with the design spec and the architect documents, and they start verification often before the RTL is even written. So start developing the they start developing the understanding, and then they start developing the test bench along with the RTL as well. And verification is a very high impact job. You find the most expensive bugs early, you protect product quality, directly influencing the design decisions. And then next is the intellectually challenging job. So every design brings new corner cases, and as the designs are getting complex and complex, the verification teams are advancing the methodologies as well. So every design brings new corner cases and failure modes. No two projects are same from the verification perspective as well. So moving forward, verification effort is substantial. So we already have discussed that more than 50% of the projects goes to verification. And similarly, the verification teams are comparable to other teams as well. And mostly it's very common that the verification teams are larger than the design teams. So in earlier stages, when design were not too complex, so designers were doing the verification stuff while doing the design. But later on, as the designs are getting complex, the design itself is a very hard job. So the designers can't spend much time on the verification, and we need to test each and every corner case. So the verification teams are required. Uh, the dedicated teams are required as verification engineers with the sole purpose to verify the chip under test. So in 2014, 50%, 53% of the ASIC design team were spent on verification, confirming that dedicated DV specialists are essential. Therefore, the verification is a very popular job in the market these days. As design complexity grows, this split between the design and verification is driving demand for engineers who specialize in verification full time with modern techniques. Yep. So moving further, so verification teams are scaling up as the industry needs more verification engineers than the design engineers. It's the high demanding career. This at this point. of era. The trend is clear. Verification teams are scaling up before 2012 or somewhere 2010. Design engineers outnumbered verification engineers. Since 2014, verification engineers have matched or exceed design engineers. And by 2014, the number of verification engineers has surpassed the verification. Verification effort scales faster than the design as the complexity grows. More transistor means more interaction, means more verification job to be done. The industry consistently needs more skilled verification engineers, and it's uh, the career that is very high in demand. And moving forward, what makes TV a strong career choice? So as we have already discussed, protect what matters. Verification is critical for safety, critical life, and it's also critical for the commercially critical products and directly protecting brand and public safety. And then a deep technical exposure as verification engineers, we get to know the technical details of the design along with the design team. We get to know the system behavior, gaining breadth that is rare in most engineering roles, and strong industry demand. So verification effort scales faster than the design complexity. The industry consistently needs more skilled verification engineers because the designs are getting complex and complex. And then the transferable skill. As verification engineers, we generally do the debugging. We develop the TBs using software techniques, hardware techniques. So we are developing the transferable skills. Uh, so the verification engineers, they may work in different teams at different levels, at IP level, at SoC level, at emulation, in pre-silicon stages, and post-silicon stages. So we have different uh, flavors to work on, and we have to develop the transferable skill. That's also a beauty in this career choice. So having said this, Ignacio, question for you. If you were talking to someone considering verification as career, what would you tell them about the skills they need to develop?
So apart from the technical skills that really matter, I think curiosity is something really important. Curiosity about how things work and how they might break. Uh, you can learn System Verilog, you can learn UVM, but curiosity, I think that's hard to teach. So this is a really important skill, I think. What do you think?
Yep. Curiosity is one thing, and I would like to add another thing. It's the debugging. So most of our time is spent in debugging the complex design with the directed test or the random test. So not just the technical debugging, but the ability to trace the failure back to the design line, which part of the design line is causing this bug to occur in this test. So I've seen great designers struggle with verification because they don't have that debugging discipline in the early stages. So they see a failure and they jump, the test is wrong, instead of systematically isolating the issue and going deep down in the design, actually. So the
Yeah.
verification, yep, the verification engineers have to be aware with the internals of the design if we are using the white box methodologies.
Mhm. Yeah. And also, I think that communication is really important.
Mhm.
As verification engineers, we need to translate between architects, designers, software teams, validation teams. So we need to understand everyone's perspective and explain the issue that we have found or the bug that we have found in terms that they understand and in terms that they care. Um, so, for example, saying this signal should be low or high at this point, it's useless to a software engineer. So we need explain that bug in terms that they understand in to explain that what that means for their code, right?
Yep. Yep. That's so true, and it connects to something else. Verification engineers need to understand the complete stack of design cycle, so from architect down to the transistors. Uh, you need to be you need to know enough so that you can challenge the design and the architect decisions. You don't need to be an expert in everything, but you need to know the complete stack in the design cycle.
Yeah, exactly.
So this slide shows the career progression in verification engineer's life. So your career path will be looking something like you are getting started at the design verification level. You will be learning new techniques. You will be uh, getting your hand dirty with the code, developing the verification environments, writing test cases, writing coverage, and in the next stage, growing as an engineer, you'll contribute to the you will on the complete block from the test plan and coverage plan perspective, debug failure, and from as you have spent some time with the code as well, so your debugging skill would have become faster, and you would have developed intuition for why a bug occur and where should start first. And as the time progress, you become more experienced. You will decide what needs to be tested with what technique, and you will be able to catch critical bugs early by deep understanding the design. You will know where to use, on what size of design you will be using the UVM test bench, and for what size of the design you will be using the formal, and what things you will be testing at emulation level. So the design verification engineers career looks something like this. So the uh, key takeaways going further, the key takeaways from this segment is verification reduces risk. So it does not prove perfection. You have to make your test plan so strong that they are covering all the essential cases, all the essential corner cases. Similarly, model designs are too complex for exhaustive testing. So UVM, constrained random verification, assertions, and coverage are powerful tools. Not guarantees that everything is verified using one. So you have to have the mixture of all these methodologies. Metric-driven verification, combining functional and the code coverage, provides a measurable path to coverage closure. Verification spans the full design lifecycle. So we have seen that the design engineers are engaged in the project at the very early stage, and then they remain with the project till the very end, till the tape out of the design. Strong verification enables confident silicon delivery. So protecting quality, protecting brand name of the company in which you're working, and the people who depend on the product. So are involved on in all these three aspects. So
You're right, Hassan. Yes, and so trying to finish a little bit here, we have covered a lot. Why verification exists, why it is important, how it works, the myths, the careers. Uh, for someone attending this webinar, is if someone needs if they need to take something from all of this, what should it be? Do you think?
right. So for me, the verification is fundamentally a thinking discipline. So in the early stage for the fresh engineers, I would always like to advise uh, question the spec, question the design, the code writing test case in system Verilog or any other language in Python. That's the easy part. So you have to think. The hard part is asking the right question to the team, to the design, and to the architect. What could go wrong? what matters most, what we are missing. If you can develop that mindset, you are on the right path of design verification.
Absolutely. I would also add that something is important is that verification is never done. You don't prove that a design is completely correct, but you reduce the risk to an acceptable level. Um, so that's humbling, but it's also liberating. It means that you are learning and that there are always new ways for finding bugs and to think about the problem.
And that's what it makes a great career choice. It's intellectually challenging, it's critical to the final product, and there's always more to learn.
Yeah, absolutely. So that finishes with our presentation. We are a little bit over the hour, so we have some questions on the chat that we can answer. But if you have any further questions, please don't hesitate to contact us at our emails that are in these slides. Um, are you okay, Hassan, if we answer the questions that are in the chat
Yep,
first?
yep, definitely.
So, Emmanuel said, I don't exactly understand the relationship between CocoaTV and UVM. What I understood is that UVM is a set of methodologies for building test benches. So it should be unrelated to the language we use to implement our test bench. So yes, UVM is a methodology, is a standard methodology that comes with an implementation in System Verilog. If you want, you can implement that methodology in any language. And CocoaTV it provides an infrastructure different than the one proposed by UVM. I think that's the main difference and relationship between them. They have different approaches on how to build a test bench infrastructure, regardless of the common programming language that you are using for any of them. What do you think, Hassan? Is
Yep,
that
I
correct? Yeah.
Yep, I think the UVM that we mentioned, that is the implementation in system the system library of UVM, which we usually run on Synopsys or Cadence tools or some other tools that are licensed. But for CocoaDB, we do not need that system library. So,
Mhm.
and the beauty, the use case of CocoaDB is it's in Python, easy to understand, and it's open source. So we can actually uh, get into the details of the source code as well.
Yeah, exactly. Then we have another question from Utkarsh. I know software-based simulation is extremely low because it models hardware behavior using software, for example, RTL simulators, where each hardware cycle require many software interactions to execute. As a result, simulation speeds are typically limited to only a few kilohertz, making it impractical to run long workloads that require billions of cycles. This also leads to low verification efficiency, since fewer test cases and scenarios can be executed within a reasonable time, increasing the risk of missing complex or rare bugs. Yes, absolutely. I have two questions. What is the biggest bottleneck in your current verification flow, simulation speed or communication overhead? And how do you balance simulation speed versus debugging visibility? I think as far as we, at least in my current job, as far as we have checked, communication overhead is not such of a bottleneck, at least between, for example, System Verilog and DPI with C++, for the reference model. This is something we are profiling regarding communication between a System Verilog or UVM test bench and an FPGA run. But simulation speed is really a bottleneck. We have a lot of simulations running overnight during the weekends, and as well as the lack of enough licenses. Yes, licenses are always a bottleneck because if not, we could run a lot of tests in parallel. Um, and how do we balance simulation speed versus debugging visibility? By applying different verification techniques. If we are verifying small designs, we usually run simulations where we have full visibility. But for example, for booting a whole OS into a CPU, we use an FPGA where we have less visibility. And trying to isolate a bug that happens in FPGA and bringing it back to simulation is always a challenge. It's really difficult. We have developed test cases, for example, for isolating parts of the OS boot process and trying to simulate that in directed test cases. Or we can use ELAS to get waveforms from the FPGA. But yeah, that's always a challenge. Hassan, anything you want to add
Yep.
to this?
Yes. So, imagine in simulation, we are limited to some hundreds or thousands of cycles, instructions. So, for example, I have a CPU on the test. So in simulation, I can increase the number of instructions to some thousands max. And if I go beyond thousands, then the simulation time would take days to complete one test. But and for even for the simple extensions in the computer architecture, if we are discussing something like vector, even more time is required. At emulation, we can run even millions and even billions of instructions altogether in seconds, in minutes, if not seconds. So emulation is so fast. But yes, the only bottleneck is the visibility. So you are running billions of instructions in one test at emulation, and if something goes wrong, you get a very thick log. So the emulation logs are usually very thick compared to the simulation logs. Similarly, the waveform files are very thick, generated from emulation runs. So you have to uh, digest that simulation log, and then you debug, then you try to reproduce the thing on the simulation, because it's easy for the design engineers to run the directed test at simulation level to verify that the design change is correct or not. So the intermediary part, debugging and identifying something from emulation to the simulation for the reproduction, it's challenging for the design, and that's there. So you have to do the.
Absolutely. Yeah, absolutely. Thanks. So we have Harun raising his hand. If you can unmute Harun, you can ask.
Okay, so thank you so much, Ignacio and Hassan. It's a wonderful uh, discussion from you guys. Honestly, I really learned a lot. I do have a couple of questions. Maybe if time allows, you can answer. The very first question is that when we talk about the metric-driven verification, so by metric, we generally means about the code and the functional things. So is this definition correct, or there are some other matrices that we must be taking care for when we think of the metric-driven verification? This is question number one. Question number two, you talked about improving the coverage with three different aspects. One is from the simulation-based verification, second is using the formal, and third is using the FPGA. And in your graphs or in the circles, you mentioned that formal is the best to get the maximum coverage, and the simulation is on the lower side. So maybe if you can uh, add some more comments that why formal is eventually the best. Uh, and why the UVM based is the lowest. And my third question, when you talked about DV as a career, like you have mentioned a lot of good things, but you haven't mentioned the financial impact of this DV as a career. So, based on your expertise, what you suggest that can DV be a good financial career for the young folks which are looking to get in this industry? Once again, thank you so much.
Okay, sure. So regarding metrics, there are a lot of things that we can measure apart from coverage. We also mentioned assertions. We can measure the assertions that were clicked, the violations of those assertions. We can also measure the bug rate. How many bugs have we found? How many have been fixed? We can measure the issues in our issue tracking tool. There are a lot of things that we can measure towards completing the verification efforts. Yeah, this is something that altogether tell us whether we have we are completely, or at least at some level, safe to tape out. Regarding your second question, if you can repeat it, sorry.
So it was formal is better than simulation.
Yes. So the thing with formal is that as it doesn't need test cases, it can explore the whole design space that we are testing. But usually formal is targeted to a very limited design space, to certain specific modules or FSMs or stuff like that. And we can cover everything regarding that module. Simulation is used for a broader or for a bigger design space. So this is why in that graph that I show, formal was covering more spots than simulation. The thing with simulation is that the design space is bigger. Maybe in the graph I should have made the circle regarding simulation bigger with less spots, and the circle for formal a little bit smaller, completely covered. Maybe that brought the confusion. And regarding economically, I think that, at least in my experience, verification jobs are at least as well paid as design jobs. And I think that as a career, it could be very well paid off. As we have seen, verification engineers are required more each year, and as design grows. So this is something that will continue to grow, and more verification engineers will be needed. And as we often know a little bit about everything, about not only RTL, but also specifications, architecture, protocols, pre-silicon, post-silicon, different methodologies. We're in communication with FPGA teams, with post-silicon bring up. Our expertise is really valuable. So career-wise, I think it can be very well paid off. Hassan, do you have any comments regarding this?
Yes. So for the first question, the metric driven verification. So you answered it very well. Coverage is one thing, but yes, there are other things that we can add. And coverage itself have so many types, so code and all types of codes, and then functional, and then assertion. So you can add as many things as you want in your metric. Related to formal, then simulation. So mathematically, formal will test each and every input and each and every scenario, but it would take too much compared to simulation. So therefore, we have to limit formal on smaller designs, and only on those designs where we think that simulation might have missed some cases. because the most common issue with the formal engineers in my team actually as well. So we hit the unconverged problems. So you gave so much big problem to the assertion model in formal verification, and now the design is not converging. The verification is not converging. So you write the assertion and you start your formal engine. It is writing the test cases, it is bombarding the design, but the list of those test cases is never ending. So that's the problem with the formal, and the formal experts are trying to address this thing, and they have advised and came up with some unique tweaks in the formal engine as well. But that's one thing. So it's trade-offs. You decide which design part you will test with formal and functional, and what design part you will test simulations and as for functional verification. And currently, the size of the design that is tested with the functional verification is way larger than the formal design. And yep,
Yes, yes.
thirdly, the financial yes, because there is a need in the market, and you have the verification engineers have transferable skills, and with the passage of time they start earning well. So uh, the basic answer is yes, they are getting good amounts, market competitive in whatever market you are. It depends. But yes, it's always market competitive because there is a need in every region. Wherever there is a semiconductor domain, verification engineers more than the design engineers are required every day.
Exactly. Okay, I think we can finish here. Thanks everyone for joining. Thanks, Hassan, for your help with this presentation and for your knowledge and for sharing this with us. And please, if you have any questions, don't hesitate to write to us.
Thank you very much.
Thanks, everyone. Bye bye. Have a good day.